You are standing at front of house, staring at thousands of raw data streams, trying to organize it all live. You have an APC40 MKII, a copy of Resolume, a pile of Claude API credits, and exactly 17 hours this weekend to build your rig. The goal is to build an automation tool that handles the tedious manual parts of VJing for you. But the open-source AV community is often a graveyard of abandoned GitHub repos and broken MIDI dependencies. Reverse engineering a complex DMX setup or emulating paid routing software like Bohm Pro can easily consume your 17-hour window without producing a working result. Python can now act as the connective tissue between your hardware and software through the Model Context Protocol. This replaces the layers of translation usually handled by third-party middleware. Mapping projects by the time they take versus the utility they deliver reveals that standard manual MIDI mapping sits in the high-time, low-novelty zone. These 3 projects fit within that 17-hour window and provide new ways to interact with your rig. Using AI to build a dynamic bridge between hardware and software context offers a higher return on a weekend build than generating static visual loops. Project 1 addresses the disconnect between on-screen visual themes and the static LED colors on your physical APC40. 3 nodes route data to the LED output. A Python script pulls the Resolume REST API for active clip metadata. Claude MCP processes this to return a 5-hex color palette. The script translates these codes into MIDI velocity values, injecting them into the controller. Your hardware updates its mood to match the visual output without any manual mapping. Directly, the 500 millisecond round-trip API latency makes this choice appropriate for ambient sets, but it is too slow for beat-matched lighting cues. In pre-production, manually verifying 148 unique MIDI button assignments is a tedious process where human error is common. You can use an MCP agent to scan the Resolume XML save file and the APC40 MIDI preset to act as an automated linter. The AI identifies specific logical errors in the raw code that are difficult to spot in dense XML files. This produces a technical diagnostic sheet that flags dead cells and overlapping shortcuts before you reach the stage. This approach eliminates hours of load testing that would otherwise happen during your soundcheck. Cautionary: without strict prompting parameters, the LLM may suggest fixes that corrupt the XML structure and break the show file. Project 3 creates custom mapping interfaces without requiring premium middleware licenses. Coding custom JSON and HTML layouts for soft controllers is usually a labor-intensive task. Instead, you can write a plain text YAML list defining your required fader and button banks. The LLM structures that list into a deployment-ready JSON interface file. This creates a browser-based visual twin in OpenStage control that syncs with the physical APC40. This setup expands the addressable control surface of a physical rig at no extra cost. AI generation replaces hours of manual drag-and-drop building. You save time on interface layout, but you rely on network stability. A Wi-Fi drop will disconnect the soft controller. These builds use AI to eliminate the data entry tasks required to program your hardware. Choosing a project depends on your primary bottleneck on this action matrix. The palette injector is for live performers prioritizing aesthetic cohesion. The patch critic suits architects needing stability for deployments. The OSC auto-generator is for users building custom UI extensions. These Python and LLM integrations share a strict operational limit. When the venue is packed, maintaining perfect synchronization and absolute system harmony is the only thing that matters. These scripts work as pre-production tools or ambient sidecars, but the critical path of a live performance should remain on native MIDI.